Looks like it's doing what it's supposed to do.
Yeah.
Cool. Okay, so yeah, when I left you guys, I left with some kind of unintelligible story about a plot that looked like this for what was going on with gravity. And I'll cut the story really short. Newton's fine. This is the plot, and the rest of the talk is going to be how I got from the leading plot to this one. So, but a bunch of you, especially RU students, have no idea what I'm talking about. So let me give you a few slides just introducing what this experiment is and maybe why you should care. So this is over in the cave back in the far side of Sempa, there's a bunch of precision gravitational experiments. And among them was this parallel plate test of gravity at sub-millimeter scales. So at distances less than about the diameter of a hair, nobody knows if gravity even happens. And this experiment was an attempt to go see whether or not it happens. As you'll remember from freshman physics, if you have an infinite sheet of charge, you can think of this as being electrostatic or mass. It's going to be fine either way. Then the field lines come straight out, and they're not born and they don't die, and that sounds reasonable. But that's only because that happens if there's an inverse square law at work. And so if the inverse square law breaks or if Gauss's law breaks, then you could have some varying force law as a function of distance away from an infinite plane of charge. And so that immediately suggests an experiment you could try. You can put some dense material closer to this sheet, some dense material farther from the sheet, and then just compare to see whether or not the pull on the two of them is the same. If it is, then Newton's inverse square law is fine, and if it's not, then maybe there's something funny going on. So, of course, you could set this thing up, and this is free to pivot in this direction. You set it up, and it's going to pick some free angle that it just sits at. So to make the experiment easier, you modulate the position of the sheet back and forth, and look to see if there's a position-correlated torque that appears on this object. And to the extent that it's done correctly, then it can be a null search for new physics. Because if gravity obeys the plan, then there's no spurious torque. This is a little closer to what it actually looks like. You have a pendulum that's hanging here. We couldn't afford an infinite sheet, so we wind up with something that's about this big. This is a centimeter. I'll show you a real picture on the next slide. And we read out the twist of this thing. It's actually a torsion pendulum that hangs from a fine thread, so it's floppy in this direction. We can measure the deflection of a laser that we bounce off of it to nanoradians without much trouble. This experiment wasn't quite that good, but that's fine. And to keep the pendulum from doing something crazy like swinging into the attractor, because the forces, other spurious electrostatic forces are big, we lock it in electrostatic feedback. And the most important addition to this slide is that we stretched a metal foil in between the sensor masses and what we call the attractor mass, that infinite sheet, to make sure that there's no electrostatics, there's no residual gas stuff. It's all in vacuum, but there are a lot of other things that could give you some trouble. And yeah, I'll get to the next slide. So this is what it really looks like. Here's this little rectangular prism is about this big, and it's hanging from a little torsion fiber. You can actually see it and its reflection in this thing that looks like a mirror, but that's actually this tightly stretched metal foil. The attractor is inside that shield. And then what I've sort of highlighted in the red line will be more apparent on the next slide is that I also have a little optical interferometer that's there to make sure that the foil doesn't move. If the foil does move, you can imagine that maybe the attractor can make the foil move, and then the foil makes the pendulum move, and then I have a problem. So that's there, and that's going to come up more. And this is what happens if you take the shield away. Now you can see the attractor hanging in there. The dark, dense stuff is tantalum. The pendulum is composed of titanium and tantalum. Tantalum has density of about 16, where water has density of about 1. And here you can see this little interferometer sticking in underneath the pendulum. So that's the quick introduction to approximately what this thing looks like. There's one equation in this talk, and this is it. So you have to have some way of parametrizing your results, and how to quantify how different this, some observed thing might be from Newton. So you notice if I completely drop the stuff over on the right, then I just recover 1 over r, which is the Newtonian potential. It would be 1 over r squared if I turned it into a force, but it's easier to work in potential. And then you'll notice that if this term and 1 have roughly equal units, or equal value, then the new physics has the same strength as gravity. So we refer to this term that I'll call alpha as being the strength relative to gravity. And then this exponential has some length scale at which it turns on, and that becomes the characteristic length. If length's large compared to that distance, you don't see it at all. Lengths are very short compared to it at that distance. It just looks like big G is bigger, and at lengths comparable to lambda, then new physics, if it's there, will show up. It's not the only way to talk about this, but it is the standard in the field, and if you want to talk about other parameterizations, we can do that all day. And I'm going to show you two different kinds of fits, just like I showed you in my thesis defense. And I guess for those of you who weren't here, I did this all blind. I had no idea what the result was going to be until all these guys saw that I had a problem. So but I did two different kinds of fits. One was something where I just decided I don't want to have a model at all. I just want to have some piecewise linear representation of the torque on the pendulum as a function of attractor position. And this is what you get if you use real error bars on simulated data that contain no signal. And so this is something where this is just kind of cruising along. This is the same kind of plot I showed you on the title slide. And if I inject a spectacular signal, then you can see that this solid line is the injection and the blue dots are the recovery. So these things kind of work. And the nice part is that I don't have to impose anything on this model. And then, so I introduced this alpha lambda space a little while ago. This is the vertical axis is this alpha, and gravity could be attractive or repulsive, whatever this modification is. So I have what looks like two plots. This is the positive alpha side and the negative alpha side. And then the length scale is this way. So if gravity did something weird around a millimeter, you'd expect it to happen somewhere in this kind of band. And depending on how big the signal is sort of its distance away from the middle. And so the way that I extracted results out of the experiment was to do something called bootstrapping, where I basically generate new synthetic results seeded out of my original data, which we can also talk about at length if you want. But basically, I do something with my data. I get a fit point. I look at it again. I get another fit point. And then the interesting thing is, where do those guys land in this plane? And this thing, it has all kinds of crazy structure. So it's handy to add confidence intervals so that you know something about what's been excluded. So if there are two different colors here, that's just kind of the error bar on. There's sort of two ways of doing it in a sense. And anywhere that's covered by both colors, definitely excluded. Anywhere that's covered by one, I could fit more, and those things would shrink, as you'll see. And then anything that's white is included. So this is, normally you're used to looking at something like this, but we usually plot it in the absolute value, which I'll show you in a little bit. This is just positive and negative alpha. And any quick questions on that before I move into showing you how things work?
There seems to be a hole in your confidence interval. What's that?
There's a hole. Oh, you mean a hole right there?
Yeah.
So this is simulated data with no signal, but it had fluctuated a little bit, in this sense, high. So there's, because you inject some random data, but there's some chance that it's not completely consistent with zero. So this is what it looks like if you begin to resolve a signal that's on one side. And you'll see more of those in a second. Yeah.
Is there a significance to that small lambda? There seem to be more negative fits than positive.
It means that this data set would somewhat favor a negative thing, but the scatter in these guys, it allows positive and negative. Because it's a log plot, it winds up being kind of intuition challenging that actually I'll show you plots in a little while where the scatter over here means that there's still stuff excluded over there even with no dots. Which is generally requires explaining. Okay, so what did I get when I unblinded? I had a plot that looked like this. And I was completely befuddled because this was not what I was expecting to see. There's some artifacts that lead to this thing having an exclusion over here, but if you just look at the distribution of the red points, you can see that this fitter was saying there's definitely something there, it's not consistent with gravity, and I want to tell you all about it. And so 10 to the 0 is alpha is equal to -1 in these units, and this is actually lower on this plot than that. So this is big compared to gravity at scales of just under a millimeter. A bunch of experiments would have seen that, and I didn't know what to do, but fortunately Ann Nelson said, hey, wait, you had that other arbitrary fit thingy, let's go look at that. And this was my first sign that something was weird. It wasn't that I executed the experiment wrong, it was that something was really strange. Because I'm expecting some kind of continuous thing, and this flyer being way out just made no sense. And the scatter, I'll show you in a second, this goes from -50 to 40 in these units, And I didn't know what to make of that either, because that was really huge. Then the big question is, well, what happened? And so and thank you guys for letting me graduate. That was great. Wait, what? Fortunately, not on my reading committee. I don't know what happened after I left the closed session, but you guys let me graduate, which is great. So actually, maybe even while you guys were still deliberating, I was sitting in the other room with Stefan worrying about this. And because now I had unblinded data, I could look at all of it. And so this is a plot of the absolute value of all of my measurements as a function of time. So this is a long time. But from this plot, I think there are 4 or 5 things that you can get out of it. One is that this fuzzy stuff here looks like that's probably the plan, right? There's some kind of scattered stuff. There's this hairy business sticking up. There's this thing, and there's that thing. And if you're really, really careful, you'll notice that these guys are a little bit higher than those guys. But that's a subtlety that's not super important. And I knew about these guys, that wasn't a concern of mine. But while I was sitting there with Stefan, this thing and that thing, I had no idea what to do with. And so it turns out that previous me had known all about this thing and dealt with it. So if the point's in black, then I'd already clipped it out with other cuts. This was the time when our laser angle sensor was turned off. And so I was getting 0 plus or minus 0. So that gives you an incredibly small signal. And so certainly within a day, I was at this level of understanding. And this particular thing was really super weird. And Stefan was like, it looks like a systematic. What systematic it is, I don't know. And so what it was is that there are 9 runs here that are systematic tests that the fitter didn't know about. And so it was systematic tests where basically I processed every run as like, okay, you feed runs into this thing and it dumps out derived results. And then later on I had some system that came along and snarfed up all of those guys and merged them into something and sent them into the fitter. And the fitter didn't know how to deal with these sets of systematic